So we're moving on to this topic called gas chemistry. And as you can probably guess, this is a topic about gases. And we've seen gases throughout chemistry so far. Now, there are quite a lot of gases to look at, if you look at all of them. So more specifically in this topic, all we're kind of worried about is the gases that you find in the air around us. And the first part of this topic is looking at what those gases are and their different percentages in the air around us. What we do for the rest of the topic is we pick 4 of the most common ones, or 4 of the most useful ones, which are nitrogen, hydrogen, oxygen and carbon dioxide. Again, very familiar gases. And we look at a number of different characteristics of them. So each of them gets their own wee section in the topic, and we'll look at them each one in turn. We look at their properties in terms of what they behave like, just physically. We look at their preparations. Preparations just means how do you make it in like a school lab. We look at their uses in society, and then we also look at how they do any chemical reactions that we might be interested in. So it's a nice topic to look at now. It's not too conceptually difficult. There's nothing really here you won't have seen before. There's not many new skills we have to pick up for this topic. It's maybe not the most exciting one of all the topics we'll look at, but you shouldn't find it too demanding or too tricky at this point in the year. So let's go on and make a wee start to the topic. So the first little section is a little introduction to these gases we're going to look at in this topic. It's called gases in the atmosphere. So the atmosphere just means the air around the earth, the air that we breathe in, breathe out. And we look at what the gases are that make up the atmosphere and their different percentages. First of all, a little history lesson for you. This idea of air goes right back to pretty much as far as human history goes back. And with the ancient Greeks, they were pretty confident that they knew how the world was made up. They had these 4 ancient elements. So before we get to these, the modern idea of all these 120 different elements making up the universe, they thought everything in the universe was made up of these 4 things: fire, earth, water and air. And if you mix them in different quantities, you get different things like hot, dry, cold, wet. And if you combine them further, you'd make different substances and pretty much everything in the universe. The person who sort of came up with the idea of air and kind of proved that air actually existed was this man here called Empedocles. He did quite a famous experiment where he proved the existence of air, which might sound like a bit of a silly thing to do or a bit of a trivial thing to do. If you think about it, it's quite hard to prove air actually exists, because you might just put it down to wind moving into your face. It's hard to know it's actually there. What he did to prove that air actually exists is something you've maybe done yourself. He got a bucket, he turned it upside down, and then he pushed it down into a lake. And he found that the bucket didn't fill up with water. In other words, there was something inside, because there was air trapped inside it, that pushed out the water that was trying to get in. And that's how he proved that air existed. So we've had this idea of air being important for quite a long time. And for many, many years, up until the last kind of 200 years, they thought it was just one substance. They thought air was air and there was nothing simpler than that. Scientific developments came about where we kind of discovered that there was different types of air, is how they put it. They discovered that there's one type of air that made fires burn really brightly. They discovered another type of air that put fires out. They discovered another type of air that caused things to explode. So quickly the idea kind of developed that maybe there was more than one gas or more than one substance that made up air. And we get to where we are today, where we've discovered that there's specific elements and compounds which are making up the air around us. These are the most important gases we've got to learn about here. The majority gas in air is nitrogen 78%. So almost 80% of the air you breathe in with every breath is actually nitrogen, and you can't actually use that in your body, it just goes in and goes out. 21% of the air is oxygen, that's the one we need to breathe and respire. Argon is one of the noble gases. It's quite a heavy one, so sort of sits down at the bottom where we are on Earth. It doesn't float off into space. It's about 1% of the air you breathe in. Carbon dioxide, which obviously everyone's very kind of worried about at the minute with global warming, it's actually a very small proportion of the air around us, 0.03 to 0.04% of it. That percentage is climbing, but it still is very low compared to the other gases around it. You'll also find other noble gases, so things like helium, things like krypton, things like neon, but they'll be in very small proportions, so we don't need to worry about their percentage. And then water vapour, which is basically what we call humidity. So if it's a very humid day, it means there's a lot of water vapour in the air. It'll depend on just where you are in the world and the time of year. So just This first section is just about setting the scene about what different gases are in air. One important thing for your exam though is, and it's quite annoying, SIA have actually specified these specific percentages. So in other words, they could in the exam ask you what percentage of air is made up of nitrogen, and you'd have to know it's specifically 78%. So these aren't kind of rough or random figures. These are the ones that SIA specify. For example, carbon dioxide, they specify it's 0.03 to 0.04%. So it's not a big deal, just make sure you learn these specific figures off rather than just learning rough figures off. So now we go through and have a look at the different gases that we find in air in a little bit more detail. So the first section we come to is nitrogen. Nitrogen is obviously the most abundant gas in air, it's 78% of it. And it's not really something you actually look at that much. You haven't really talked that much about nitrogen so far in what you've looked at in chemistry in school. First thing we come to is its kind of physical properties. It's a colourless, odourless gas, which you might expect because you can't taste it, you can't smell it, you can't see it in air. It's insoluble in water, so it doesn't go into the oceans or anything, it stays in the atmosphere. There's a missing third point here, it should say neutral. So in other words, if you bring it towards water, it doesn't make it turn into an acid or alkaline solution, which kind of goes along with the idea it doesn't dissolve in water. You're only going to make an acid if something does dissolve in water, but we call it a nitrogen, a neutral gas. Next bit is its reactivity, which is also kind of do with its physical properties. Different to pretty much all the other gases in this topic, nitrogen stands out because it's very, very unreactive. The reason it's very unreactive is to do with its structure or its bonding. Now we have looked at nitrogen so far earlier on this year. We looked at the bonding in covalent bonding. Nitrogen is one of those examples of a triple bond. It's quite unusual. So each nitrogen's got 5 electrons in the outer shell. Therefore, if they share 3 pairs in the middle, that gets everything up to 8, get the full outer shell, which is stable. These 3 pairs in the middle are referred to as a triple bond. The consequence of a triple bond is it makes that structure there, this bond, very, very strong and very, very stable. In other words, it's going to take a massive amount of energy to get it to break apart. I'm pretty sure, I think nitrogen's triple bond is actually the second strongest bond in the universe. So it's really, really strong. If you think about the implication of that, if you want to try to react nitrogen to make something else, the first point of any reaction is breaking the bonds in the reactants to get them to bond something new. So it kind of stops any reactions happening because you can't really get to bond anything new if you can't get to break the bond in the middle in the first place. So the implication of that is that nitrogen is a very unreactive gas. The explanation for that is got a very strong triple bond that takes a lot of energy to break. So not many gases have triple bonds, only a couple of them. Because it does have a triple bond, it means that nitrogen is very unreactive and very stable. We see that kind of idea of it being very unreactive come back in the uses of nitrogen because whilst it doesn't really do much, in some cases that can actually be quite useful for us in terms of how we apply it. One thing you've probably seen before is liquid nitrogen. So here's a little kind of picture of that. You've probably seen those viral videos where they put different things in liquid nitrogen and they freeze instantly. Liquid nitrogen is very cold and is therefore used as a coolant. So if you are harvesting sort of vegetables or things like that and you want to keep them fresh, you want to freeze them very quickly. One way of freezing them very quickly is to dip them into liquid nitrogen, which cools them right down instantly and freezes them, keeps them nice and fresh until you want to use them. The second use is that nitrogen provides an inert atmosphere in food packaging to keep food fresh. So something you might not have realised before, if you look at lots of food, particularly like meat and things like that, you probably see in the package a best before date, and the best before date might be for a week away. So it might last for a week in your fridge. What you probably see in the small print is it says once you open it, you should use it within a day or two, which sounds a bit confusing because why can it stay fresh in the packet, but once you open the packet, it goes off very quickly? The reason is that most food is packaged in a nitrogen environment. So if you take anything that's sort of been sealed off, it's not air inside it, it's actually pure nitrogen. Because nitrogen doesn't react with anything, it means it doesn't cause food to go off or oxidize as air would cause it to go off. Therefore it helps the food to keep nice and fresh until you open it, obviously, and air gets in and it starts going off. So it's used in food packaging as well because it provides what we call an inert atmosphere. Inert meaning it doesn't react. The final one is in the manufacture of ammonia, which sounds like a very unusual use. Ammonia is very important because it provides pretty much all the fertilizers that keep us alive as humans. In other words, keeps our crops growing. Ammonia is quite a useful fertilizer, or used to make fertilizers, but it's quite hard to make it. The main source of making ammonia is to make it from nitrogen gas, which is what we look at. So with that kind of final use, we kind of get into a wee subsection. One important use of nitrogen is to make ammonia. Let's look at ammonia in a bit more detail now. So ammonia we have come across before. It's got the formula NH3. We looked at it in covalent bonding just. It's a little bit different to nitrogen. It's a colourless, pungent gas. Pungent means it has a strong smell. It actually is soluble in water, and it's also more dense than air. And the reason we're so interested in ammonia, I've already mentioned it, is it's one of the most important fertilisers, or it makes the most important fertilisers we use on the planet. And scientists kind of knew for a long time that ammonia would be quite a useful material to make. Unfortunately, it is actually quite difficult to make. The reason that it's difficult to make is because this is the main reaction we use. We react nitrogen with hydrogen to make ammonia because that's the two things that make up ammonia. But as we've already established, nitrogen is very, very unreactive. It's very stable. So it's actually quite hard to force it to react with hydrogen to make ammonia. All that changed when we came up with this thing called the Harbour Process, which was invented by a scientist called Fritz Haber. It's quite an interesting story behind it. This reaction has saved more lives than any other scientific discovery in history, probably. If we didn't have artificial fertilizers, we would only be able to support about 6 billion people on this planet in terms of being able to grow enough crops for them. As you probably know, there's about 7 billion people on planet Earth. So that extra billion people we can feed comes from the use of artificial fertilizers. You might think, brilliant, this Fritz Haber guy, he must be this great scientist who made this great discovery for humanity. What's interesting is that when he was making this process, or designing this process, it wasn't for fertilizers. He was a scientist during the Second World War, and he was making this process to develop ammonia, which can also be used in explosives, used in the German war effort. So the process was discovered as a way of making explosives, but then they used it afterwards to make fertilizers to keep people alive, which is quite ironic. But anyway, what the process is, it's reacting nitrogen with hydrogen to make ammonia. And you just have to be careful by the balancing there. So 2 nitrogens, 3 hydrogens, 2 ammonias. One important thing about the process is that it's reversible, and that's actually another reason why it's quite hard to do. If you do get nitrogen and hydrogen to react together to make ammonia, it can actually go backwards as well. Ammonia can break apart to reform the reactants. So whenever you see those wee kind of arrows where it looks like one's pointing one way, one's pointing the other, that means it's a reversible process. And we'll look at that in a wee topic called equilibrium later on in the year. In terms of how the Harbour process works, there's a couple of conditions just to be aware of. It uses quite a specific temperature, 450 degrees C, so it has to be quite hot. It uses a high pressure, so we haven't really talked about pressure before. The pressure it uses is a pressure of 200 atmospheres. You might not have seen that unit before. Atmospheres is kind of a way of explaining pressure in terms of comparing it to atmospheric pressure. So the pressure we're currently under from all the weight of the kind of atmosphere above us is known as 1 atmosphere. It's the reference point. So in other words, we have to put it at 200 times the pressure of atmospheric pressure in this process. Don't worry about that, you can just call it 200 atmospheres. We use a catalyst to speed up the process as well. It's called an iron catalyst, just chopped up really fine. And that will make us our ammonia, which is useful for fertilizers. Another wee thing about ammonia, how you actually prove you actually made it. I can't remember if I've shown you this so far this year. You've got a very specific test for ammonia. If you think you've got ammonia gas, what you do is you get a glass rod, you dip that glass rod into concentrated hydrochloric acid. It has to be concentrated for it to work very well. And then with your kind of damp glass rod, which has been dipped in the acid, if you hold that glass rod into what you think is ammonia gas, you will see a white smoke. And that's your observation. That white smoke will only form if you've got ammonia gas. It's the only one that will react with hydrochloric acid in that way. The equation for what's going on there is just the two things are reacting. The ammonia reacts with hydrochloric acid to make what we call an ammonium salt, which is ammonium chloride. You could be asked for the balanced symbol equation there. So just converting all these words into symbols, ammonia we've looked at is NH3. Hydrochloric acid, should remember quite well, is HCl. Now, ammonium chloride, we haven't really looked at ammonium salts that much. We did look at them very quickly in the acids topic. Ammonium is just an ion based on ammonia. It's a positive ion, it's NH4+, it's on the back of your periodic table. Chloride is just normal chloride, Cl-. If you swap and drop that, you just get NH4Cl. And that actually is balanced as it is. So it's a strange reaction and you're only getting one product, but that's all you have to put down there. So we've looked at ammonia being an important use of nitrogen. It's used in fertilizers, and we have got a test for it. Now, just to build in a bit on the uses of ammonia, so again, as we mentioned, it's used in the manufacture of fertilizers. As ammonia is a weak base, it can react with acids to form ammonium salts. So I've been harping on about ammonia being important. Ammonia itself isn't actually the fertilizer you spray on crops. It's the salts you make from ammonia. So in other words, you react ammonia with an acid, it makes a salt, and the salt is a really good fertilizer. So there's a number of ways you can make that salt, and it basically involves reacting with different acids. The only acids we're worried about is the ones we've studied so far. Hydrochloric acid, we've seen up here already, sulfuric acid and nitric acid. So there's three potential equations you maybe could be asked for how they make ammonium salts. So the first one is, well, we've already kind of looked at the first one. The test for ammonia is also a way of making an ammonium salt, ammonium chloride. So that could be a reaction to make a fertilizer. Ammonium chloride could be a fertilizer itself. A second one would be ammonia reacting with sulfuric acid to make ammonium sulfate. That would be another example of ammonium salt that could be a fertilizer. Simple equation, NH3 for ammonia, H2SO4 for sulfuric acid. Ammonium sulfate, just do my swap and drop here, NH4+ for ammonium, SO4 2- for sulfate, swap and drop, gets me NH4 twice, SO4 once. To balance that, I need a 2 in front of that NH3 there. Third one, ammonia plus nitric acid, so NH3 plus HNO3 is nitric acid. Do my swap and drop, NH4 plus, NO3-, again these are the back of your periodic table. Swap and drop them, we just get NH4NO3. And that's actually balanced because we've got one of each. These salts are very soluble in water, therefore they can dissolve in soil to help plants absorb the nutrients, specifically the nitrogen nutrient. So that's probably the longest class we have to look at. So going back to the start, very quick recap. Nitrogen is a very kind of boring gas. It's very unreactive because it's got that strong triple bond. It takes a lot of energy to break it. It's therefore used in kind of coolants to keep things frozen, used to keep foods fresh because it doesn't react with foods. But probably the most important use is it's used to make ammonia, which is another gas. Ammonia is a useful gas because we use to make fertilizers. So how we make ammonia is using this special reaction called the Harbour Process, where you react nitrogen with hydrogen to make ammonia. And we looked at the conditions for that Harbour Process. We looked at a test to actually prove if you've got ammonia, if you think you've made it, which involves making a white smoke when you dip a glass rod with hydrochloric acid into ammonia. And the final thing is, well, how do you use ammonia to make those fertilizers? The answer to that is you react them with acids. If you react ammonia with an acid, you make what's called an ammonium salt. There's three types: ammonium chloride, ammonium sulfate, ammonium nitrate. And those salts will actually act as your fertilizer when you spray them onto soil.